Alright, so welcome to the continuation of our previous video. So remember, in our previous video we calculated the forces, these two forces. So today, just a quick reminder of what we're dealing with, or what we are required to do. This is how our question reads like. It reads as follows. Calculate the cross-section dimensions of the wooden beam below using the conditions of normal stress, given that the limit of the bending strength of the beam is 16 megapascals. So this is our limit of the bending strength. So today, what will we be dealing with today? Our task today is to determine the maximum bending moment, mx. This will be our task today, and this is very important because it takes us a step closer to what we are looking for, the value of h, the dimensions of this cross section. So what do we do in order to calculate the value of the maximum bending moment? So basically, the value of the maximum bending moment is calculated by using what we call the method of cross sections. So we'll use the method of cross sections to determine the value of the maximum bending moment. Using this method of cross sections, we are going to draw what we call internal force, I prefer saying load diagrams. So in order for us to calculate the maximum bending moment, we're going to use the method of cross sections. This method of cross sections helps us to determine the to draw the internal force diagrams. So yeah, this is what we'll be doing today. We'll be drawing internal force diagrams. Just a brief background. Internal force diagrams basically show us how the forces are distributed at a specific cross section. For example, if I was going to cut my beam at this point, the internal force diagram will show me the kind of forces that are acting specifically at this point. So in this case, this is what we'll be doing. For us to draw the internal force diagrams, we have two diagrams. The first one is a diagram that represents the forces. So I'll draw a line here. Draw a line. I'll draw a line and say Q, Y. This is a positive and then this is a negative. So basically, this diagram here that I've drawn will be representing the forces. And then we'll also have another diagram that will be representing the moments. So in this case, we'll begin like this. To make things easy, what this method, the method of cross sections, entails is that if I make a certain cut here, let's say I cut at this point, I say this is my first section, I can tell that from this point here up until this point, there is nothing new that I can see. So the forces that are at this point are the same as the forces that will be at this point, and those that will be at this point are the same in this beam. What the change that I see next is after this point. So I'll draw this one here as my second, and I'll also draw this one as my third section. And then when I come here, I'll put one section here, just slightly after this point, and then I'll also have another section here, which will be my fifth section. Sorry, this case will be my fifth section. This is what we do. Let me find the small paper that I'll be using. This is what will be happening. The method of section goes like this. If I cover here, I only write what I see. So whatever I've covered here does not affect the beam in any way. So in this case, when I cover here, the only force that I'm seeing is this 21.3 kilonewtons. And then I look at the way it is moving relative to this paper that I'm using. So if I stand here, this point here will start moving in the anti-clockwise direction. In this case, anti-clockwise will be equal to negative, and then clockwise will be equal to positive. So at my first section, Q11, what I see is negative 21.3 kilonewtons. Using an approximate scale, I'll plot this negative 21.3 kilonewtons. Let's say I'll put it on my diagram here. I'll put it somewhere here and say 21.3. If I come to my next section here, I do not see these 12 kilonewtons yet. So we can see from this point here, from this cross section up until this point, there's nothing new that I can see. So I'm going to say Q11 is equal to Q22. So this one here, again, I'll move, and this one will give me a rectangle like this. So this one here again is 21.3. Just a few basic rules. When you're drawing, just the moment you see that there's just a fixed point force, you know that on your force diagram you're going to have a triangle. If you have a shear spread out force like this, you're going to have a rectangle in this case. And then if you're having a shear spread out force, you're going to have a rectangle. On the moment diagram, we'll get there and I explain what you need to expect. So here we can see that this one here is giving us a certain rectangle with a negative sign, and then I'll shade. This is shading, yeah, something like that. The moment I cross this point here, I can now see that this 12 kilonewtons has become visible. So my QY33 becomes equal to this here. This 12 is moving clockwise in the clockwise direction, so it gains a positive value. So it will be 12 minus 21.3. 12 minus 21.3 is 21.3 gives me negative 9.3. So here, remember, this line here is representing both the second and my line here is representing both the second and third sections. So in this case, I'll move a bit here. This is where my 9.3 will be, and then I can tell that QY33 is equal to Q44. So this one again will be a rectangle like this. It will have a negative value here. Let me just shade it with a red pen. Okay. So I have something like this. And then when I get to this gets interesting. When I get to Q55, what I already have a negative 9.3 kilonewtons, because we're taking everything that we're seeing. So at this point I can see the negative 9.3 kilonewtons. And then the new thing that is happening here is that what I have now, I have 13 kilonewtons that is being spread out along a length of 3 meters. So what I'll do here is this 13 kilonewtons, if you can see, it is moving in the clockwise direction. So if it is moving in the clockwise direction, remember we said it is a positive value, so therefore it will become 13 times 3, which is 39, which is 39 point, sorry, this is just 39.0 kilonewtons. So when I add these two, 39 plus negative 9.3 gives me 29.7. This is specifically true because when I look at the force that I'm having here, I'm having 29.7. So it does not matter whether I start from here, this force here should flash. The force that I will calculate in my section 5 should be equal to the force that is at this particular point. So here I'll get into my positives. I have 29.7, and then like I said, you obtain some sort of triangle. So I have this triangle here, and I also have this triangle because I'm having a shear spread force here. So here I have a positive, and then I'll have a negative here, and then I'll shade. Alright, so we've calculated this, but to make things easy, I can do this and quickly see that this force here, it is moving in the in the clockwise direction, so it will be having a positive value, which is true as we have calculated. So basically, this is how you plot a diagram for the forces that are acting on a bulker. Bulker is Russian, sorry. Beam. For the forces that are acting along a beam or on a beam. So yeah, so we've plotted this diagram. The next video will be showing how to plot the moments for this force. Sorry, the moment diagram using the method of sections.